So let's get together here, and so the first part of today's session will be essentially continuing where we left off. So as you remember, we were talking about basics of the POTS model. We're talking that this is minimization, a scheme, Monte Carlo minimization, energy minimization scheme. And right now I want to do some exercises that will build your intuition in terms of like what this energy minimization looks like in practice. So we'll start with something very, very simple. We'll build a simulation with the single cell, and we'll play with contact energies first. And we'll see what's going on. You'll get some intuition. I will explain what's going on based on mathematics. And then hopefully this will give you some ideas of how to start playing with parameters and what to expect from POTS model. Sometimes if you see some irregularities like self-fragmenting, you might be puzzled why they are doing this. I'll try to explain this, okay? All right. So what I'm gonna do right now is actually create new simulation. Let me close this one. And it would be good if you can follow along. So close project. So right now what I'm gonna do, I'm gonna go to CC3D project, new simulation. And I'm gonna call this simulation single cell. All right? Because we'll start with single cell. For the purpose of this exercise, I'm gonna make lattice smaller. I'm gonna make it 100 by 100. Yeah, and then I'll move to the next tab. Continue. And I said I want to have single cell, so I just need one cell type. So let's call it, I don't know what we call this cell. Cell A, as we did before. Right? So nothing fancy here. I'm not going to be adding any chemical field. I'm not going to be adding, well, I will add actually. So what I'm going to add here is contact energy. Okay? Only contact energy. Because we're going to start with the simplest possible simulation. Well, yes. And I want to teach you a little bit of, I want to give you a little bit of intuition, like how to deal with contact energies. So, because I think this is the, let's say, the most difficult part of the POTS model, understanding contact energies and what they do. So, so let's start with contact energies only. So perhaps this is not the simplest Hamiltonian, it's not the simplest mathematical formulation, but let's say it's one of the simplest, one of the simpler ones. And I'm gonna finish it. So now, let me open up, I'm not sure, here. I'm gonna open up another terminal and start player from that terminal. So I will load the simulation that we have. And by the way, perhaps you discovered this, but if you right click on the project here, there is this button open in player. You can start your simulation here, right? I can do that, and hopefully it will open. So the player opens and simulation starts playing. But maybe this is just an old habit. I prefer to have player started from independent terminal. So I'm gonna do that. So the nice thing here, and I wanna tell you one more thing here. The nice thing here is like, once you start the simulation, the next time you open player, this simulation is preloaded. I mean, so you don't have to go and navigate through the file dialog, because those file dialogs are hideous on many platforms. Mac is particularly bad, but all of them are not nice to interact with. There's lots of clicking. So it's sort of like nice to know this because all you have to do right now is just hit play and this will play again. So same simulation. And again, if you've noticed, there is a recent simulation submenu where you have recent simulations. If only 3 of them show up. If you want more, I can show you how to do this. So if you want more recent simulations, you click configuration and you go to general settings and number of recent simulations. You bump it to, I don't know, 10, let's say. Hit OK. So now player will remember up to 10 recent simulations. So again, configuration, general settings, and bump the number of recent simulations. All right. So this is interesting so far. We've built our simulation. We have one cell type, and they all disappear. Why do they disappear? Does it matter now? Because we didn't put any volume constraint, right? Remember, previously we had the same problem. The first simulation that I showed you, cells were also disappearing. So remember, we went and what we did in code, we just added, we set lambda volume and target volume. Do you remember that? So that kept cells from disappearing. We're not going to do this here. Instead, we're going to do something different. So first of all, I want you to go to edit, open up this, yes. Yes, medium is overwriting cells. Absolutely, yes. And once, so if you have a single cell, and once the last pixel of the single cell gets overwritten by medium, the cell is removed automatically. So there's actually a trigger in CompuCell 3D that if cell volume reaches 0, the cell is gone. So the actual physical object is removed, and memory is freed for that cell. So that's how it's set up. All right. I'm not sure, I'm going to make this a little bit bigger. Can everybody see this? So I want to start with a single cell. So towards the end of the XML, we have this uniform initializer. And probably if you know what uniform or blob initializers do by now, right? Blob initializer will create a circular blob of cells, and uniform initializer will create rectangular blob of cells. Nothing fancy here, really. But I'm going to remove this altogether. So what I'm going to do, I'm going to highlight everything from the last steppable tag from here up to here. And if you prefer, I can change the, I'm not sure how well, no, let me actually switch to different color schemes so that you can see it better. Where was it? Configuration. Now, I forgot where it is. I wrote it here. Style config, default. I believe this is. Let's leave it like that. So I'm going to remove everything from here to here, right? I don't want it. So now if I start the simulation, obviously, let me start. Oh, yeah, you can. So, yeah, so I can, that's a good point. So, Stefan, a good point. So let me show you how to comment out. So I'm going to undo what I did. So Control Z or Apple Z does undo. So if you want to comment out, so here's the thing. This is how comments, so this is original. Actually, let me. So this line here, when it says initial layout of cells in the form of rectangular slab, this line is a comment line in XML. So in XML, let's say if I want to comment this element, what you do, you put exclamation, 2 minuses, and if you want to end the comment, you put 2 minuses. And this comments everything out. A lot of typing. So there is a shortcut. There is a shortcut. So let's say I wanna comment out this part. So I'm gonna highlight everything, and I'm gonna go to edit menu, and there is block comment. And it will do it for you. But there's a problem with this approach, and I'll show you what the problem is. And this is the problem with in general with commenting stuff in XML. So let's say I want to comment entire thing. I'm going to highlight everything. And I'm going to do comment again. So here's the problem. Everything looks nice except here. Well, it is probably not, I don't think, I mean, maybe there are some better editors. I mean, I'm sure there are, but most of them probably will make this mistake. They will insert additional closing tag for comment in the commented already line. Not in the Mac? When you say not in the Mac, meaning in like, this is a Mac. But are you using Twedit? Yeah. Oh, sorry. I'm glad. I mean, what can I say? But no, there is. Yeah. And I think, maybe we can try doing this in PyCharm. PyCharm, by the way, has also great syntax highlighting for XML and other languages. But here's the problem. So the solution to this is just remove this line altogether, this initial layout, and we can comment it out like that. This is perfectly fine. Now I'm not, yeah, Stefan, I think you're right. We can leave it here. Oh yeah. Yeah. Yes, like that. And then let's try this. Okay.
Yeah, I like the whole thing.
Yes.
The whole paragraph. Do a comment.
Yes.
And then uncomment.
Uncomment everything?
Uncomment that whole thing and recomment.
Oh, sorry. I see what you're saying. Okay.
Uncomment again.
Right.
And then recomment.
Oh yeah. So that was essentially what I was doing differently. Yeah. But I get what you're, yeah, exactly. That will work. Excellent. All right. So maybe after this commenting and uncommenting exercise, we'll move on. And again, you saw already that if I run the simulation, there is no cell. I did it on purpose. I don't want any cell. So I want to show you how to create cell in Python, in case you don't know. Quite frankly, those initializers, they're handy sometimes, but more often very often they are kind of not very flexible. So if you learn how to lay out cells in Python, you're probably in a driver's seat. So this is how I'm going to create cells. I don't remember this syntax, quite frankly. So this is what I'm going to do. I'm going to go to CC3D Python menu, and I think cell manipulation menu has a bunch of options. And one of them is create cell. I'm gonna pick it and press it here. So it inserts the code snippet. So I'm inserting this code snippet in the start function. So let me do it again, in case you missed it. So I'm going to my steppable file, and I'm placing a cursor where the code should be in the steppable file in the start function. So this is my cursor. I'm going to CC3D Python menu. I'm going to cell manipulation, and then I'm creating create cell. Right? And then the code gets inserted. And then the nice thing is that it says the size of the cell, there's a comment on top of the code, which says size of the cell will be 3 by 3 by 1. So this is interesting. So what happens, what's going on here? Let's look at this left-hand side. So left-hand side is a template, but this function new cell is a function that every steppable has. Right-hand side, sorry. Yeah, other left, yes. Thank you. Yeah, I've been spending too much time in the rooms with the mirrors, so I'm getting confused. But the right-hand side, exactly. So new cell is the function that creates a cell object. So this function will create object for the cell. And what you do here, what you pass is a type number. I can do 1 because I have only one cell type, and the cell type ID for cell A is 1. So I can do that, or I can replace 1 with the label that says self.cell A. So every steppable is aware of what cell types you defined in cell type plugin. And it knows the names of those cell types. Now, if you capitalize every single letter in the type name, so capital C, capital E, capital double L, and capital A, and type self, cell A, all capitals, this gets converted to 1. So this syntax or this syntax are equivalent. Your choice. I prefer the latter. Like that. Let's run this code. Let's see what happens. I'm going to just hit start and see if it works. And it's always a good idea to sort of like, when you're writing code, make changes incrementally. Don't write 100 lines of code because it's, you know, it's a waste of time, quite frankly. So just do things step by step, and, you know, every programmer does it like that. I mean, there is our cell. It's kind of tiny, right? And it's in the location, it's not in the center of the lattice. So let's move it to the center of the lattice. So my lattice, it has, it's 100 by 100, so center is at position 50. So I'm gonna change this number. So I think you're familiar with the slicing operator, right? So this is what the statement says. Take the cell field, and for positions, for the following positions specified by slicing operators on the cell field, assign to those positions new cell. So in practice, it works like this. CompuCell creates one cell object, and the pointer to this object, not a copy of the object, the pointer to this object is assigned to every lattice position. Okay? That's what it is. So I'm going to change it to 50, change it to 55, 50, 55. And I'm going to save and run again. And where is my, oh, sorry. So now my cell moved. All right, so you see what I'm saying? So what's going on here? This is X position, this is Y position, this is Z position, right? So what I'm saying is that along X axis, cell will occupy pixels from pixel number 50 to pixel number 55. And 55 not inclusive, I believe. And from here, it will go from 50 along y-axis to 55. So we were creating a square, 5 by 5 square. So far, so good. Let's run it. Cell disappears. So now I'm going to do something different in the XML. I'm going to go to XML, and I'm going to change the contact energy cell A and medium to -5. I'm going to change this one also to -5. So what I'm saying is the following. If there is interface between cell A and a medium, so let's go back here. Let's go back here, and let's make it a little bit bigger so you can see what's going on. So if there is interface between medium, the black space, and the cell, I'm assigning for every single pixel along the boundary, I'm assigning value -5. So for every single interface, right? And this will be my energy. So I have a bunch of those pixels, so I'll have a bunch of -5s. So my energy will be -75, for example. I don't know, I'm guessing. Now, according to this statement, if there is another cell A, right, and they touch each other, then for every interface between two cell A's, I'm going to also assign -5. That's what it is. So now, having said that, and knowing that CompuCell 3D minimizes energy, right? So it tries to drive energy to minimum. Can anybody guess what the outcome of the simulation will be? Yes, exactly. So let's do this. I'm going to hit stop because I need to restart the simulation. And this is what this, let me actually unzoom a little bit so that you can see access. And this is how the simulation looks like. That's your single cell. You start with a pixel or, I don't know, 20 pixels, and all of a sudden, after a few Monte Carlo steps, you have this giant mass. And notice, if you zoom in, as you said, cells will do whatever it takes to maximize the surface, right? So there is this labyrinth, right? Cell pixels are interleaved with medium pixels because for every interface, you minimize energy. And this will happen. So now, exactly. So that's what I wanted to show you. Essentially, start from like the very simple. Does it make sense? So, in other words, you are putting energy terms, and then you are randomly flipping pixels. And CompuCell has one objective, to minimize energy. If every single energy component is negative, it will try to create as many components or as many interfaces between cell and medium as possible. So this is the result. Now let's do the opposite. Let's flip, yes, there's just one cell. And you can tell that there is one cell. How can I tell that there is one cell? This is a very good question. Well, if you go to the output, to the console output, you see step number 1310, cell inventory equals 1. So 1 means one cell. Yeah. So, okay. So now if I go back and I flip the energies to +5, well, you will get the behavior that you want, right? I mean, you will get you will get the behavior that you're familiar with already. Cell will disappear for the same reason. Now, all energies are positive, right? So in order to minimize positive energy, you want to create as few interfaces between cell and medium as possible, right? That's it. So now, it's a good question. So there was a suggestion about volume constraint. Surface constraint. We'll get to surface constraint, but what's going to happen if I introduce volume constraint? And so I have negative energies. I have negative energies. So again, right now, cell will spread like crazy. Now, where is the cell? Oh, I didn't save. Exactly. Really, it's annoying because I have to implement autosave. I'm used to editors that autosave things, and but it does not. So let me run it again. So if I introduce volume constraint, first of all, how do I introduce volume constraint? Look, if you look at in your XML, there is nothing that says volume, right? So we need to insert volume constraint. And there are two ways to do that. You can either type, you can essentially copy this line, like this, center of mass, put end element marking. So end element mark is this / greater than sign, and type volume, right? So this is one of the ways. Let's do it, and I'll show you next time with the surface. I'll show you another way. This is just volume constraint. It's exactly, yeah, exactly. So you can say, so they are in exactly. So numerically, area and volume in 2D are equivalent because in CompuCell, actually, 2D simulation is a 3D simulation, but the thickness of the cell is 1. So numerically, it's correct. Yeah. So let me, it's a good point. Let me do this volume constraint. I'm gonna, again, if I run it, cell will also get crazy because I only specify that I want to load volume constraint, but I did not specify volume constraint parameters. I didn't say what target volume and lambda volume is. So I have to go to Stepable, and right after I create cells, I can, you know what, I'm gonna show you a different way of doing this. So I'm gonna do a little bit cell 1, close. I'm gonna show you something different this time. Because normally you've learned that in order to set volume constraint, cell 1, you iterate over all cells, right? That's the pattern that you see always. But right now we are dealing with one cell. Sometimes, not always, and especially if you create cells in Python, it's so convenient to maybe, when you create cell, store it in a local variable, cell1. Use this local variable to initialize cell field, and use this local variable to set target volume equals, I don't know, I'm gonna set 50, and lambda volume will be 2.0. Let's do it like that. Save it. Let's run it, stop. And let's run it. Interesting, huh? So it's a different simulation than before, right? Still, cell is highly fragmented, but it doesn't occupy entire lattice because we have volume constraints. So there is a constraint that will prevent number of pixels from going beyond target volume too much, right? On the other hand, we have contact energy that tries to maximize contact area, right? So there are those two opposing forces, but obviously that's not desired outcome, right? Because the cell is still fragmented. So let's use the suggestion. It was raised before, yes? This is sort of like, so this exercise essentially doesn't show so much biology. It shows, so like mechanics of the POTS model and like some, just to build some intuition so that you know what each energy term does. I mean, of course, you know, if you look at this and you can sort of imagine, but it's like a good idea to start with something very simple and build up. And that's maybe something that we should have done yesterday, but it's still Tuesday morning, so we're fine. So that's a good point. Now, so in order, we can try surface, right? So let's try surface constraint. So I'm gonna go to XML. And do we wanna keep volume, Julio, or we wanna get rid of volume? Just keep surface. Get rid of volume. We'll just have surface. So now I'm gonna, so one thing I can do, I can essentially do this. Right? That's fine. But I want to show you another way. I wanted to show you this CC2D-ML menu. So at the beginning of the lectures, I said that you can specify entire simulation in Python, or you can keep XML. And XML, whatever you say, it is clumsy. I mean, it's nothing something to get excited about. But the nice thing about XML is that it's structured. And in particular, we have this helper menu that inserts every single syntax for every single plugin that exists in CompuCell. So for example, if you're lost, if you want to edit single cells, if you want to edit your XML and you don't know the syntax for plugin and you don't want to look up the manual, why would you? I mean, I don't look at there that much. I'll go here, surface, and it inserts. Interestingly, notice that it's already aware of cell types, right? So that also helps. It's particularly helpful when you have to rewrite contact energies and you have 10 cell types and many interactions. So, well, let's say that's helpful. So, sorry. So now it inserted this syntax. But you can say, hey, before you only had surface, now you have some extra surface energy parameters. What's the difference? Well, here's the difference. No. I'm just like indenting it like whatever. Doesn't matter. It's good idea to keep things tidy, but it's not important. So here, if we run the simulation, every single cell of type A will have the same lambda surface and target surface. So if you're fine with that, if you're fine with the situation where every single cell of a given type has the fixed parameters, you can use this syntax. If you want individual cells to have different parameters, it is best to get rid of this and put end sign for the element and initialize everything in Python. You know what? For now, let's keep this. Right. Now we can run it. I'm going to leave this as it is. Although, actually, no, I'm going to actually increase it to 5,000. Where? Nowhere. So in XML, there is nothing about cells. But here, in the single cell steppable, there is start function. And here, I'm creating a cell. So I'm creating manually a single cell. So if I don't have this code in start function, there will be no cells. So I wanted to show you that it's perfectly okay. And maybe we can do an exercise. And I can ask you to actually create, I don't know, some crazy patterns of cells in your in Python. It's easy. So that's where it is. So notice, I increased this target volume to, who knows how to count zeros? 500,000, right? Yes, this I can say. This will be okay. Oh, and by the way, we can try this in XML. That's a good point. So let's try it and see if it runs. Okay. So my target volume is huge. Huge. Did I say right? I didn't say right. Wow. Let's run it. What's going on? Can anybody explain to me what's going on? I put target volume 500,000 and cells don't grow. Why? Plugin, exactly. I did not see, again, I'm sorry for being like kind of pedantic about this, but this is one of the common sort of like questions, mistakes, you know, people forget about it. If you don't specify that if you don't include this line, if you don't include this line with volume, Compusel will not load volume plugin, right? So you can, sure, you can modify those target volume and lambda volume, but they have no effect whatsoever. Now that I've included, well, now that I included that, see that, right, now let me uninclude it. Let me remove this and still leave 500,000 target volume. It doesn't work, right? You can call plugins, that's correct. You can load plugins from Python. The problem is that, well, there's no problem. You just have to be aware that each plugin has to be initialized. So you have to pass simulator object to the plugin, and I think simulator object, and then parse XML. So call parsing function. So call XML parsing function of the plugin from if you have such, right? If you have XML. But it's perfectly fine to write a plugin that doesn't take XML, right? But has functions that where you manually set in Python parameters, and then you can do that. So it's a little bit advanced topic. Actually, I have another tutorial for how to write C++ steppables, and one of them actually does exactly that. So, all right, so does it make sense so far? Still, cell gets right. So we have to play with. We have to perhaps make the energy, sorry, contact surface smaller. Let's see if this will work. No, it doesn't. Let's do that. All right, so now cell stays together. And of course, there's this competition between contact energy and surface energy. So contact energy, because all coefficients are negative, so contact energy tries to maximize surface. The surface energy tries to constrain surface. So sometimes you get those fragmented patterns. So one way to deal with a cell that tries to fragment like this is to include connectivity plugin. And maybe this is a good idea actually to introduce connectivity plugin. It's not the best. So I want to just make this clear. Connectivity plugin should not be used as a common way of keeping cells from fragmenting. You have contact energies and volume and surface constraints to achieve this goal, right? Connectivity plugin is used usually as a last resort, when nothing works, and for example, you want to have elongated cells. That's when you use connectivity plugin. But it's actually a good idea to actually show you how connectivity plugin would work on this simulation. So let me increase surface to 100 maybe. And let's see. So we have this spaghetti-like cell in two pieces, right? This is still a single cell, even though this appears as those are two cells, this piece and that piece, they belong to the same cell object, right? How do I know this? Well, I know this because inventory is 1. So this number doesn't matter really. I can put, so this number doesn't matter. So in other words, we never consider medium to medium interactions. I can put it to 0 and you will get the same pattern. So right, so that's a very good point. This is, in fact, let's try and see what's gonna happen if I remove it. It's not gonna change anything. That's right. So this number essentially doesn't matter. However, right. Yeah. The sign. Yes. Yes. They don't record. They will actually try to create as many contacts. They will stick to each other. Yeah, but we don't have a cell A and cell A right now, right? Because we have only one cell. So in other words, let me show you this. No, this is only for, so contact, so that's a good point. So contact energy is only between two different cells. So in other words, if I have a single cell like here, I'm not gonna be counting internal pixels. So yeah. One cell. But it can be fragmented, yeah. Just as we saw before. Remember this pixelized cell or this cell that was just creating this big labyrinth when we had no surface constraint? This was still one cell. Yeah. Yeah. Yes, exactly. Well, exactly. The so the yeah. So the way to deal with that is choosing proper contact energies. And typically, Julia, correct me if I'm wrong, we work with positive contact energies and we put volume constraint. So if you have positive contact energies and volume constraint, this usually keeps cells compact. And we can do this exercise. But let's say you work with negative contact energies and cells are prone to actually fragmenting. I don't know, this one doesn't want to fragment, it's a bad cell. Right. Like, oh, that'd be good. You know, no, this is a good point. I mean, this would be nice to have like this visual editor yourselves. Yeah. You cannot do that. You can do what you can do it programmatically in Python, but it's not the same as clicking, it's clumsy. But yeah, no, this is good. So see, I wanted to actually build interactive way of teaching pods where you can, as you said, you can graphically inspect cells, you can right click and it will say, oh, this is exactly. No, this is, I see that this will be valuable. So maybe for next year workshop, we'll have something like that. Because I feel like, you know, there is some learning curve to this. I mean, I'm not gonna, you know, we can show you complicated simulations and, you know, show you how to code them quickly and say, hey, this is easy. But in fact, you know, there is a learning curve. So you need to understand just those basic sort of like principles. Once you understand that, you can really scale up and you can use Python. But I feel like, no, this is a good suggestion that having graphical way of editing cells and inspecting cells, and inspecting manually. So like, you know, if I right click here, it should be a pop-up. Cell ID 1, right click here, cell ID 1. Then you know. Right now, I'm telling you, go here and check. And by the way, yeah. That's annoying, yeah. Yeah. Correct. Yeah, you don't want to do this. Yeah. I mean, normally, it's not a problem because normally the way people write computational simulations, it does, first of all, most of them will use positive contact energies, volume constraints, and they build simulations based on small segments. They pick a subsystem, they understand how it behaves, they add another component. So what is subsystem? Subsystem can be growing cell, right? Cell that grows. What is another subsystem? Vasculature, right? So you build separate vascular model. And then you connect them to and say, hey, you know, maybe I can build vascularized tumor, right? And actually, this type of exercises, what we're doing previously, what I was doing previously, led to, from single cell, I can show you all the steps, what it takes to build vascularized tumor. Maybe we will do this today, maybe tomorrow, because we have planned for today. But the idea is that. Mm-hmm. It is. So we had this tool called CellDraw that is still, you can still use it, but it requires older version of CompuCell. So in other words, you can install older version of CompuCell like 3.75 or 3.76, whatever, because you can have two versions on your computer. And it will generate so-called pixel initialization file format. So it's PIFF extension. And then exactly, imports image, and you can either paint manually or you can get image and it will do, I don't think it does segmentation, but I think you can manually click on pixels. So it is possible. This tool is a little bit old. We haven't touched it in many years. It exists, but maybe it's a time to actually refresh it. Yeah, exactly. And this is actually important because this is one of the sort of like easy ways how you can create a tool that potentially could be shared between multiple platforms. right? So there's CompuCell 3D that takes this file format. But then you can load the same image in another tool like Morpheus or Chase. They take different formats, but you can have a common tool, this CellDraw, that will output different formats depending what you want. So there is a lot in terms of standardization of those tools. Standardization of multi-cell models is very hard. I mean, people are spending careers, literally careers, trying to standardize description of ODEs, like, well, I shouldn't say ODEs, but reaction kinetic networks, like SBML community. And I know how much effort goes there, and they did a lot of good work, but it's a lot of hard work. Now, those type of models are way, way, way more complex than reaction kinetics. Why they are more complex? Well, because you're not dealing with ODEs. ODEs are actually small components of those models, because we can put reaction kinetic networks in a single cell. Those models that we're talking about have cells. Cells have shapes. You have diffusion equation, reaction diffusion equations, and on top of that, reaction kinetics. So it's a little bit of a zoo, but I think we can take some baby steps and implement, as you said, this visual cell layout initializer. All right, so connectivity plugin. Let's try to rescue this situation with connectivity plugin. And how do I, well, I don't remember syntax for connectivity plugin, but I think, let's try this. It might happen it will crash. I wouldn't be surprised. Hold on. It doesn't. So previous versions of CompuCell actually required you to specify contact energies between all pairs of cell types. I think the new version is smarter in the sense that it initializes all contact energies to 0. So if you don't specify contact energy between given two cell types, right, Julia? Or maybe, let's do an experiment. Because quite frankly, I was expecting a crash here. And for a good reason. So here's my philosophy for software. It's much better for software to crash than keep running and printing silent warnings and giving you wrong results. I mean, I'd rather have, that. And that's, having said that, software crashing is not always a good thing, and perhaps there should be a better handling mechanism. So let's try. So I'm gonna create a bunch of other cells. So I'm gonna create adjacent cell. This will be 50, 60, 5, 60, and I'm going to create the same cell, A. Notice what I'm doing here. This statement return a cell object. I call it cell 1. Now I call this statement again. Now this statement will return different object, right? Because think of it as a factory, right? New cell creates, each time you call it, you get new cell. So there is no, even though this looks the same, those are different cells. So those two cells touch each other initially. Let's see what happens. Oh, I forgot to save it. What else? The volume of the first cell. Say it again. Oh yeah, I know, but I don't care about target volume because I don't have. So as a matter of fact, let me remove this so that it doesn't cause any confusion. Let me save it. I was expecting a crash, quite frankly, because old versions of CompuCell would crash. Because if you have two cells next to each other and you don't specify contact energy between them, old CompuCell would crash. This one doesn't crash because, as I said, all contact energies are initialized to 0. So it knows what cell types you have. It creates this contact energy matrix and it populates zeros. So maybe the crash was better. I don't know. Yeah. That is important. That is important if you have more than one cell. Because no, medium can be only one. So medium, first of all, in CompuCell 3D, let me start the simulation again. So we have those two cells. And notice that initially, let me do it again, they touch each other by corner. So they are not in contact. So there's like, they're like that. Medium is an empty space. So medium as a cell does not exist. But you can think of medium as a cell with unconstrained volume. So in other words, like, think of medium as, you can, yeah. But then you have to create physical cells and you would have to manage their, their properties, like volume, target volume, surface volume. So what CompuCell does and what most or every pod simulator does, it treats medium as a special type of cell, even though there is no cell object underneath. So each time you detect that there is a boundary of cell with medium, with vacuum, so to speak, you assign to this boundary contact energy. But other than that, medium does not exist as a physical cell. Does that make sense? So the only thing you can have with the medium, the only interaction is the contact energy. There are no other interactions. Medium doesn't have volume constraint. Medium doesn't have surface constraint. So let's go back to this question. So first things. I'm gonna remove this line with where I specify cell A, contact energy. Actually, you know what? Tell you what. I'm gonna remove it and I'm gonna run simulation. Sorry. Okay, let's remove this, save it. So those two cells essentially, they don't do anything. They fragment. I don't know which part is from which cell. That's a good point. It would be nice to have visual hover over effect. But now I'm gonna do something different. I'm gonna change this contact energy between those two cells to -50. So now what I'm expecting is that there should be a lot of cell-cell interfaces. So my original start point is this, right? And now, because this energy is -50, I expect those two cells to create as many boundaries between themselves as possible. And let's see if this is the case. And I feel like it is the case because you see those lines here. Those are the lines that separate one cell from another, right? And I can run the simulation further and you should see that there should be a lot of those squiggly lines will turn into a checkerboard without actually, let's run it for a while. And it doesn't because of the surface constraint. But you get an idea, right? Yeah, I have surface constraints. So surface constraint will make sure that there should be. So there are two competing mechanisms. One tries to maximize the surface, but then there is surface constraint, which prevents from happening. Does that make sense? All right. No. Cell type ID is one, but cell ID. So there are two IDs. One is type ID or cell.type, and this is the type. So we have two cells of type 1, but those are two separate cells. So inventory, if I go here, should be 2. And for some reason, I'm getting this ugly printout here. Cell ID equals 1, cell ID equals, I don't know where it's coming from. I kind of think I know. It's from here. Yeah. I also want to show you how to get a pixel of the lattice and see what cell you get back. Boundary conditions. This is not periodic boundary conditions, but we can add them, and I can show you how. Yeah, let's go step by step. There are a bunch of demos with. So let me actually show you. You know. I'm trying to find something. I'm trying, maybe let's try it. I'm going to show you how to find all the files with extension .xml that have periodic boundary in it. Okay, just because there is a bunch of demos. There's like 200 demos with every CompuCell distribution that you get for you get them as a part of every installation. They're not always like super sophisticated demos that rather teach you techniques. But they are a good starting point for exploration. So let me show you how I do this using, for example, TwoEdit. So I'm gonna go to find. So first of all, I'm going to edit and maybe search, find. I'm gonna click this tab, find and replace in files. For those of you who used Notepad++, I know how many of you use. Actually, when I wrote this tool, I wanted it to be a cross-platform clone of Notepad++. So this dialog is actually almost verbatim taken from this other code. And let's hope it works. So this is what I'm looking for. I'm looking for word periodic. I'm not going to be replacing with anything. My extension is XML, and I want to find, and this is the directory that I'll be searching. So I'm going to go to the place where I installed my CompuCell, and I believe demo. I think this is where we are. Demos. I'm going to pick this directory. And I'm going to find all. So at the end, after you do this, TwoEdit will populate a bunch of simulations where I used word periodic in XML. And first of all, it teaches you how to set up periodic boundary condition. I don't know. Let me choose. I'm just looking for something useful. Oh, this one is actually good. Connectivity test. I'm going to double click here. And it should open file, okay? So the nice thing is that when you open this, you get you get this little thing, boundary X. So along boundary in X direction, there is no flux condition, but along, oh, that doesn't make sense. But then I override the previous statement with periodic boundary conditions. So this line is superfluous, another bug. Actually, this bug is benign. I mean, it doesn't do anything. And again, just for reference, this output looks almost the same as Notepad++. It was fun programming it. All right, so let's go back to our simulation. And let's let's change those guys from being positive, from being negative to being positive. Now, let me remove Surface plugin and replace it with, and I'm going to replace it with, what am I doing? Volume constraint. So I'm putting volume constraint. Actually, you know what? I'm going to do it like this. I'm going to be lazy, and I'm going to use CC3DML, plugins, volume. Fine. I get some default settings. I'm going to stick with them. No big deal. Let me run it. Now, our cells look more like what we would like them to look like. But there's an interesting phenomenon. Look, let's actually create those cells so that they touch each other. I didn't do a good job first, because I should have kept this one like this, okay? So initially, let me zoom in, those cells touch each other, but after a few clicks, they stop touching each other. So previously, we had opposite situations. Cells were just like, wrapping around each other. Right now, they hate each other. And again, this is all it is. It's essentially a manifestation of energy minimization. Why? Because every energy here, every contact energy is positive. So if you have positive contact energies, the way to minimize energy term due to contact energy, you want to create as few interfaces as possible. And notice, if you have interface between cell A and cell A, it costs you 50 units. So we want to get rid of this interface. And that's why, so here's another thing. If you want cells to repel each other, you bump up contact energy, right? You increase contact energy. You keep everything positive, but increase contact energies. And if you want cells to stick to each other, what you want to do? Well, all you have to do is just lower contact energy and replace it with 1. So now we should see different situations. Now we should see situations where cells will stick to each other because they don't want to be sticking to the medium. They don't want to be surrounded by medium. They want to stick to each other because contact energy between cell A and cell A is 1 now. So you have a method, right? If you want, it's less than a medium, right? So it's the relative hierarchy that matters. So this is the rule of thumb that sort of like is important to actually implement, for example, cell sorting. Maybe we can do this exercise, cell sorting. James said he hates cell sorting because it's a confusing exercise. And maybe, for the beginning, as a first exercise, it's confusing. But I think right now with this explanation that I gave you, maybe it's not so much confusing. So maybe we'll do something soon. So, and let's see what's going on here, sorry. Yeah, so they are sticking with each other. So how about this? How about I take the simulation? So first of all, you know what? Let me save this simulation. I'm going to post it online so that you have this for a reference. It's a simple simulation. And I'm going to create new simulation for cell sorting. How about that?